My name is Massey, and for the final project, I chose to create a program that would solve the Nurikabe problem. Now, the Nurikabe problem is a game that gets its name from this creature in Japanese folklore that is said to stand or sit or lie in pathways, and that's an invisible creature. People try to get, to the other end of the path, they bump up against it, they can no longer proceed. And this sense of suddenly inexplicably being unable to proceed down a path was used as inspiration for the name of this game, and you'll see why in a moment. Now, the game itself is this grid. You can see it kind of looks like Sudoku, but is really in practice very different. There's these numbers in here. And now what these numbers represent are how many should not be shaded, how many squares. So imagine that you are shading in certain squares here, like with a pencil or pen. Certain ones should not be shaded. And so let's say this 2 means there need to be 2 not shaded, and including this 2 one, which will not be shaded because that would cover up the number itself, and these must be contiguous with one another. So let's say 2 contiguous squares would be like this right here, including the 2. That's 2 contiguous squares, and so those ones should not be shaded in. And now diagonality does not count as contiguous, by the way, it's worth mentioning. And so one thing you might notice is that these ones could be in a contiguous white block here that's not shaded in, this 5 and this 3. Well, that would automatically break one of the rules, though, because is it going to be an unshaded part of 5 blocks or squares, or is it going to be 3? So that derives then from that principle another rule that numbered squares cannot be a part of the same unshaded block. So they must all be in their own kind of separate area. And from this, since they're all separate, they are called islands. So they're distinct. They're an island of their own. And then they're surrounded by these shaded in squares. They're all shaded, and we call those water squares. And so the basic rules are, as said, there must be a specified number of white squares in these islands or unshaded squares in the islands, and these islands can't touch with one another, they can't come into direct contiguous contact, and each other square that's not a part of the island must be shaded in. It's called water squares because it's not a part of the land. And then these water squares also, there's more rules. These water squares themselves must be all contiguous with one another, and there may not be any 2 by 2 space, so a 2 by 2 space with squares that are all shaded in or water squares. So here's a perfect solution. You can see here much better than the little kind of sketching I was doing on the image earlier. This is a area where there's 6 squares all connected with one another there, and the same for all the others. No 2 by 2 area of water. All the water is connected. And now that is an NP complete problem, but also you can ignore the water connectivity rule and it still be NP complete. You can also ignore the 2 by 2 the prevention of 2 by 2 areas of water, and it also be NP complete for that. So you can see here are examples of variations where the answers aren't like the ones we saw before, and they're still NP complete. And this is not how the game, I believe, is normally played, and yet the problem is still, that NP complete difficulty to find. I chose to use that second variant where I allow 2 by 2 pools of water, but still disallow water disconnectivity. So the method used was to, of course, use the genetic algorithm followed by an aggregative wisdom of crowds algorithm afterwards. So for the genetic algorithm, there had to be an initial population created, a population of grids. If I use paths throughout this presentation at any point, I mean grids. This the traveling salesman thing is so ingrained in my mind. I occasionally slip up and I'll say paths, but what I mean is grids. And so grids are created by getting the correct amount of white squares that are needed in there. And from that, we can see the 7. This means that since this one's always white, it's always going to be that way. It's never going to be shaded in, these number squares. The 7 means there need to be 6 more connected to it white squares. This 2 means there need to be 1 more. This other 2 means there need to be another 1. We continue in this way, getting the sum, and then we know how many white squares need to be on the board. They are placed almost completely randomly, with the only rules being enforced is that, and these are very easily enforceable rules that are enforced throughout the entire run of the code, and it's just that there cannot be a white square place where it'd be adjacent to two numbers because that would connect them again, break rules. And then there may not be one place to the top, bottom, left, or right of a one square, because then that would make the one island bigger than it should be. Again, very easy to check for the size of that island. It's harder to check for the sizes of other islands, and so we penalize first. Then in order to get a fitter population, we first have to determine what's more fit, what's less fit. And so what is done is there are three rules that are observed. There is the rule that the islands must be a proper size. They cannot be too large or too big. Islands cannot be connected, and water must be connected. So if any one of these rules is broken, there is a penalty assigned and a cost is added to. So let's say an island is missing three squares that it should have, three blocks that it should have. Well, we do +7 for each block it's missing, or if it has too many, +7 for that. And then if there are ones connected, every time there are two number squares a part of a single island, we do +2 to the cost, and then also +13 to the cost for each disconnected body of water, more than there should be. So there should be one, but if there's a second area that's disconnected, then that's 13 to the cost, and then 13 to the cost, there's yet another one, so on and so forth. And the only part where this is different is basically at the end, where we just want more of the proper cost of just more discrete violations without it being weighted in this fashion previously described. And so at the end of the genetic process, it's just +1 for each violation of island size and +1 for each violation of water connectivity. These grids are then passed into a function that separates them into fitter and less fit halves, and then the crossover method used is to look at discrete islands from one parent or another, because they're fit paths paired out to be parents, have children created from them, children grids, and then you take part from one, part from the other. And so first you look at an island, which is denoted by that sort of anchoring number square. So let's say there's a 7 number, and let's say there's only one 7 number in the grid, and we look at that 7, and then flip a coin, sort of in code form, and choose one parent to draw that island from. So whatever ones are connected in one of the parents, those squares are then transposed into the child, and we keep doing this with all of the other islands, transposing islands from a random one of the parents for each needed island until they're all in the child. And then there's a sort of cleanup procedure done after that, where if there's too many or too few as a result of this sort of messy crossover procedure, too many or too few island squares, that is, they are subtracted or added from the child grid. And there's also a mutation function, and somewhere, I suppose, during the extensive commentation process with the code, I ended up deleting the 2 or 3 lines that actually do the mutation, which was just to take blocks and swap them, basically. And so that ended up being deleted from the code. The actual swapping part of it is still in there, the function, and stuff's passed into, but nothing's actually done with it. And then I realized that afterwards, after the submission, is now fixed, but a little bit too late with that fix there, and thought that was just worth calling out. And then there's one generation complete. This process keeps going for many generations, and then the single best path from each generation is then singled out, and then this whole process is run many, many times until we have a whole new population of the best outputs of each run of the genetic algorithm. Then the aggregative wisdom of crowds part needs to find a sort of a consensus among these. And so it's similar to like a voting system where they each cast their vote for whether a certain block should be water or should be land. And then, so the more fit paths, or grids rather, their answer is given more weight than other less fit grids. Then to help derive consensus, this sort of beta normalization process is, or rather function is called, which is called the package. All the logic that is really done behind the scenes. And this is called many times this aggregative algorithm, with these beta parameters being passed in, so different sort of consensus grids can be returned by it. And then each run of the entire code, 16 consensus grids are created, each one with created with different beta parameters. And then the best of these is given as the answer to the problem. And for the data, I looked online, looked at different Nurikabe problems you could find in websites where you actually get to play the game, or images, or something of the sort, and represented them in code format by using a sort of matrix nested list structure. And for water, I use 0 to represent water, -1 to represent non-number land squares, and for the numbered squares, I used simply, the correct number for them. And so the data set I used the most was a 10 by 9 grid. I used others, which I mentioned in the project report. And then, so how well did the genetic algorithm part of the code do? Well, on the 10 by 9 data set, which was the largest one I used, a perfect solution was found roughly 2.6% of the time, and much more often with the 6 by 6 grid. Now, by the time the aggregative algorithm was called, a lot of times with the 10 by 9, a perfect solution was already found. However, sometimes there wasn't. So, the hope is that the aggregative algorithm would end up putting out sort of, or being a refinement stage after that. So there would always be a perfect one, no matter what, no matter how bad, or, no matter if there was or wasn't a perfect solution among the genetic algorithm outputs. The 6 by 6, of course, did much better. And the wisdom of crowds part, however, on the 10 by 9 never found a perfect solution. The genetic part did. Then, after all of this, with the aggregative algorithm being called in, a perfect solution ended up never being found for that. The 6 by 6 it did, but however, the outputs of the genetic algorithm on the 6 by 6 grid were so good that the aggregative algorithm really kind of already had its work done for it. Now, what I believe caused this issue was that, in that Project 5, the paper that was included in the Project 5 description, the people who were doing their wisdom of crowds algorithm ended up using a heuristic afterwards, after each after aggregation, to clean up the aggregated solutions. They used the Lin-Kernighan heuristic. On the last project, I used a greedy approach to sort of clean up the path and make them good. This one, I tried to use a greedy approach. It didn't end up working, and then, of course, there wasn't time to really do a new approach, so I just deleted the greedy part of it because it wasn't doing anything, really, and then we were left without a sort of end cleanup heuristic after the aggregation. However, since then, since submission of the project, I've had time to test another hill climbing algorithm on it, using these to clean up the aggregative grids, and it actually has performed very well. And while this is not necessarily germane to the project itself, the project that I submitted, it is more, it sort of means that the broad approach is actually very promising for solving this sort of problem, this sort of grid problem, and that perfect solutions can be found very frequently. And so each full run of the code, there's 16 aggregative grids. Of those, 37.5% of the time of the data that I've observed have been perfect. So very, very promising. Of course, remains to be tested more on larger data sets, but the general approach, I think, is worthwhile looking into more. And so, as a sort of summary, the genetic approach works fairly well on relatively large data sets. And given the right heuristic, I believe that the aggregative wisdom of crowds solution can give very good answers to this sort of problem, and that it could also be adapted to other similar grid problems, just as long as different games have different sort of things that need to be penalized. But if one figures that sort of penalty process out, I think that it could be very easily adapted to similar problems. Thank you.